Okay, 0, 0. 1, so 0, 0, it's going 0. Then 1, 2, 3, 4, 1 second, it's going 1, 2, 3, 4, 5, 6, 7. Boom, right there, right? At 2 seconds, it's going 14. Boom. Now my scale's messed up, so I'm going to go ahead and do it by 2s, because otherwise I'm going to run out of space. Does that make sense? So we do it by 2s. So this would be 3.5, 2, 3.5. So my second one, and so this is my Seagull's 3.5. Boom. So this is my Seagull's 128.
Okay.
It's going faster every second. Agreed?
Yeah.
We realize that we can't calculate the normal way, which is what everybody in the front row is trying to do. They're trying to say 7 meters per second, you go 7 meters. But I'm not going constant 7, I'm going starting at 0 and going to 7. So I'm only going to get half of that, which is why the triangle works. Right? My average speed would be 3.5. If I start at 0 and at 7, average speed is about 3.5.
Can you say that like slower?
Okay.
Wait, what's the question?
If my speed is 0. Okay. Imagine I'm sitting in a car going 0, and you go by me at 7 meters per second, I hit the gas pedal. If after 1 second we have the same speed, are we the same distance? Why not? I start at the same time. As soon as you hit the starting line, I hit the gas pedal. We're together.
I was already going. No, you're not.
I'm not going as fast as you for the same amount of time, right? So therefore, I'm going to go less distance. And the way we calculate that is we say if I'm going from 0 to 7, okay, it's just the area of the curve.
Wait, what was the question that you answered? Why is it?
How far?
How far? Okay.
How far?
So how far?
So the slope of the velocity time graph is 7, because that's the acceleration. The area of the curve is the displacement. Make sense? That's what we're doing. And so I'll just keep going here, make sure I've got all these data points that I really want. This is 35.
She's going to be traveling at 3.5 meters every second.
No, no.
Just for the first one?
This is the first one, 3.5. Then after that, I'm already going 7, then go to 14. So I'm going to go a lot farther, right?
Yeah, but if you...
Well, yes, but the idea being if I'm already going faster, I'm going to go farther. Right? My acceleration is the same, but when I accelerate, if I'm accelerating, the first second, I don't go as far as I do the second or the third or the fourth, right? Because I'm going faster and faster. Does that make sense?
Yeah.
Yeah. Yeah? Okay, good. That's that idea. That's an acceleration displacement thing that we started with that we kind of got good at, and then we kind of have to start thinking about different terms. Okay, so there's the Seagull. Let's do the Puffin. What's the Puffin look like? Puffin's doing 9, but Puffin doesn't do anything for how long? 2 seconds. So the Puffin's first 2 seconds look like this. And then it goes up at 9. 1, 2, 3, 4.5. There's 9. There's my second one that's at 18. That's 27. Color was the first one, red or brown were the 2. So 2, 3, 1. Unfortunately, it just went off the graph. Darn it. Huh. Okay. So far, so good?
Yes.
All right. Anybody disagree with that? Those are velocity time graphs, right? Okay. So how do I figure out when How am I going to figure out this race? This cone. How do I know who wins the race?
By calculating who gets to 15 meters first.
Figure who gets to 15 meters first. Got to be careful though. I might get to 15 meters first, but if the seagull catches me before I get up to speed, I might be faster at the end, but it wouldn't matter because I'm already eaten.
So wherever they cross.
So wherever they cross in terms of displacement. So I'm going to start looking closely at where do they cross. Okay?
Okay.
Where were their displacements cross? Is this a displacement time graph?
No.
No.
So
Now I do know if they don't catch by the time these graphs cross, I'm never going to catch the whatever the cute little Puffin.
Puffin.
I'm never going to catch it, right? Yes.
Like after we do this, I tried it a sort of sketchy way to figure like over that after.
I would love to try it a sketchy way. Sketchy ways is what this is physics, man. We live in sketchy land. All right. Oh, didn't want to do that. Okay, so let's do this. Let's set up a table. Whoop, whoop. I've got time, I've got Seagull, and I've got Puffin, and I want to know where they are. Agreed? Now, this is a little tricky because there's a how far they went, and then there's a where they are, right?
Yeah.
So now I'm going to have to think about this, and maybe I give myself a little more room to write in this table. So I'm going to have a category for where. I'm going to have a category for how far. Terrible. I can't even write. The pen's not working. Okay, whatever. How far, and then I'm going to have where. Does that make sense? How high above the water, right? And this is Seagull, and this is Puffin. Agreed? All right. Well, we're going to count from this. I can calculate how far it's gone. But then I'm going to have to subtract it from 110 because it's not really, I need to know where it is in terms of how far above the water, right? Yeah. Okay, so looking at time, I got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I might need more spaces than that. I doubt it, though. Okay, so let's look at Seagull first. Seagull. After 1 second, it has gone 1/2. 7 times 1, that'd be 3.5. Agreed? Which means it is 110 minus 3.5. Where's that? 106.5 meters. Our Seagull has gone 0. Sorry, Puffin's gone 0, and it's still sitting at 60 meters above the water. Is that where it started? Okay. I've got the wrong worksheet. That's why I can't find where it says that. Not on this side, it's not on this side. Okay, got it. Okay, so far so good. You may have a problem so far. Okay, so let's do one with, oh, that was 0 seconds. I messed that up. That's 1 second, isn't it? Crud, that's terrible. I apologize. You don't see you're looking like I just did something horribly bad. That's 1 second, right? It was not 0. 0, they're at 110 and 60, right? I apologize. Okay, so let's do 2 seconds. So that'd be 1/2, 14 times 2, right? Which would be 14 is how far it traveled. And 14 from 110 makes me at 96 meters, right? Starting to get ugly. And the Puffin is still taking a nap. Agreed? It starts at 2, but hasn't gone anywhere. For the first 2 seconds, it goes nowhere, right? Now, 3 seconds, hopefully things are going to change for the Puffin. It's a good thing. So I'm actually going to hop out to 4 seconds, okay with everybody? Because it doesn't look like we're close yet. So at 4, it'd be 1/2, 4 times 28. So that'd be 2 times 28, which is 56. Agreed? 56, which means from 110, that means I'm at 54 meters. Oh, this Puffin's dead. Send out a card. But the Puffin has woken up. 1/2. 2 times 18, right? So that'd be 18. So it's gone 18 meters. So it's sitting at 42 meters. 12 meters in closing. Pressure's on. Now what? Looks like we're close. Should I go by 1 second now?
Yeah.
Let's do it. So at 1 second, so this would be 1/2 5 times 35? 1/2 5 times 35, and I get 87.5, right? So 110 minus that, I'm at 22.5 meters, dead Puffin. This is going to be awful. Puffin would be 1/2 27 times 3, right? So 1/2 27 times 3 would be 40.5. Well, because at 5 seconds, it would have traveled for 3 seconds, right? Yeah. So 19.5 meters. Well, Puffin's not dead yet. Do you want to try 6 seconds? Let's try 6 seconds. At 6 seconds. Now, we're kind of got off my graph here. To get 5 seconds, we did 1/2 35 times 5, right? To do the one before, we did 1/2 28 times 4. So what would the next one be? 1/2 42 times 6. I'm glad you said that. Is anybody else not? I mean, that's just math pattern, right? So that would be 3 times 42. It's 126. Well, it's in the water already. Okay? So that may not be good enough for us to figure it out, right? So now I got to look back carefully. Now, how am I going to do this? 5.5 seconds. So now, here's where things get dicey. And this is where you guys are good mathematicians. When you walk in the door, that's what we check, right? It's what I checked on you. I said, can you do math? Can you do problem solving? Can you think there's a problem? How do we do 5.5? Wouldn't it be 1/2 5.5? What's my pattern? 5.5 times 7. I'm looking right at you, and you're not smiling at all. Okay, so this is 1/2 4 times 7 times 4, right? 1/2 5 times 7 times 5. 1/2 6 times 7 times 6. What would 5.5 be? Because now we want to look at something more closely. How fast would it be going at 5.5 seconds? It'd only go up 3.5 from where it was before. So it'd be 3.5 more than this, which would be 38.5. Or you could do 5.5 times 7. Okay? Everyone with me so far? So now I'm going to back up because 6 was too big a number. And I'm going to start picking other numbers. So I'm going to try 5.5. At 5.5, I've got 0.5 times 5.5 times 38.5. And I got 105.875 minus 110. That's 4.1 meters. That's still too far, is it not? Is it not too far? So I'm needing to back up. So how do I get a smaller number? Now I'm going to ask Miss Redfern. So if I do 5.1, how do I figure what this number is? 7 times 5.1. Beautifully done. So 35.7. So that would be 0.5 times 35.7 times 5.1, and I get a lovely 91. 5.1 is 91.035 minus 110. That's when it gets to 18.9 meters. Did it catch it by then? How am I going to check the Seagull? How am I going to check the Puffin? Same sort of thing. It's going to be 1/2. It's going to be 9 times 5.1 times 3. Oh, sorry, 3.1 times 3.1, right? Because it's 2 seconds off.
What? Because it started 2
2 seconds.